Let's look at a couple examples of writing and evaluating Riemann sums. Before we do that, just a reminder of what the Riemann sum is. So the Riemann sum is just the sum formula that we came up with for the approximate area under the graph of y equals f of x between the x values a and b. So we wrote out the Riemann sum for right-hand endpoints. So that's f of a plus I delta x times delta x, the sum of that from 1 to n. Here I'm using delta x just as an abbreviation for the width of one of these rectangles, which was b minus a over the number of rectangles, n. So delta x, just that's the width. So wherever you see delta x, just think of the width of one of these rectangles. So right here, that's delta x. And they all have the same width. So we worked out right-hand endpoints, which looks like this. The formula for left-hand endpoints looks essentially the same. The only difference is that instead of I starting at 1, I starts at 0. And instead of going up to n, you go up to n minus 1. So the reason for this is for right-hand endpoints, your first endpoint is one step to the right. And so I is the number of steps that you're taking to the right, so I needs to start at 1 to get to this first right-hand endpoint. And to get to the last right-hand endpoint, you have to take n steps, and so that's why there's an n here. For left-hand endpoints, on the other hand, your first left-hand endpoints is 0 steps, and so I has to start at 0, and your last left-hand endpoint is at n minus 1 steps, and so that's why there's an n minus 1. But other than that, the two formulas work exactly the same. So let's look at a couple examples. So here's one. Let's approximate the area under the function x squared on the interval from 1 to 3 using 4 rectangles and right-hand endpoints. So since we're on the interval from 1 to 3, we know that a is going to be 1 and b is going to be 3. And we're using 4 rectangles, so n is 4. All right, so we can work out delta x right away. Delta x is b minus a over n. So that's 3 minus 1 over 4. And that's a half. So our approximate area is approximately the sum from I equals, since we're using right-hand endpoints, we're going to start at 1 and go up to n, which is 4. And it's f of a, which is 1, plus I times delta x, and delta x we worked out is a half, times delta x, which again is a half. So this is the sum from I equals 1 to 4 of, now we need to write out this function, but f is the squaring function. So it's 1 plus 1/2 I squared times a half. Okay, so to get our approximate area, this is the sum we need to evaluate. And, you know, there are a couple different ways to evaluate this. Maybe the most straightforward way is to just plug in your different values of I and actually evaluate all of this. So I'll write that up here. So when we plug in I equals 1 into this pattern, we get, so 1 plus 1/2 is 3/2. So that's squared times another half plus, so this is the I equals 1 term. And then for our I equals 2 term, we get, let's see, 1 plus 1/2 times 2. So 1 plus 1 is 2 squared times a half plus. And then for the I equals 3 term, we get 5/2 squared times a half plus. And then finally, 6/2 or 3 squared times a half. Okay, and then we could do all this arithmetic to come up with our approximate area. I want to evaluate this in a slightly different way because the only reason that it's actually practical to write out this sum explicitly is because there are only 4 terms. You can imagine that if we wanted to do this, but with this 4 being much larger, we wouldn't want to actually write out all of these terms because it would just take too long. So instead, what we can do is use the properties of sigma notation that we figured out. So here we have a constant multiple inside of our sigma, so we can move that outside of our sigma. That gives us 1/2 times the sum from I equals 1 to 4 times 1 plus 1/2 I squared. Okay, now the stuff inside of the sigma is a little bit simpler, which is a little bit nicer. Okay, another thing we can do is actually multiply out this squaring. So that's going to give us 1/2 times the sum from I equals 1 to 4 of, let's see, 1 plus, that's going to be I plus 1 over 4I squared. If I multiplied that out correctly, which hopefully I did. Okay, and now we have some additions inside of our sigma. So we can distribute the sigma. Remember, we're not actually distributing. What we're actually doing is using associativity and commutativity of addition, but it looks like we're distributing that sigma. So we get the sum from I equals 1 to 4 of 1 plus the sum from I equals 1 to 4 of I plus the sum from I equals 1 to 4 of 1 over 4 times I squared. All right, well look, we have a 1 over 4 inside of this sigma. It's a multiple inside of this sigma, so we can move it outside. Okay, and now look, we have a sum where the pattern is just 1. We have a sum where the pattern is just I, and we have a sum where the pattern is just I squared, and all of these sums start at 1. We have formulas that tell us exactly what these give us without having to explicitly compute the sums. So it was 1/2 times. So the sum from 1 to 4 of 1, our formula told us that it's just whatever this top bound is, so that's 4, plus the sum from 1 to 4 of I is, it's this top number, which is 4 times 4 plus 1 over 2, plus, and then 1 over 4 times the sum from 1 to 4 of I squared, and the sum of the squares is, it was, right, this top number, we called that n when we wrote down this formula, but the formula was n times n plus 1 times 2n plus 1. Oh, I need to be writing 4s though. Let me back up. 4 times 4 plus 1 times 2 times 4 plus 1, 2 times 4 plus 1, all divided by 6. Okay, and you can see that this has given us an expression that we can evaluate, just do all the arithmetic here, and we'll have our approximate area, but it would be realistic to evaluate all of this even if our number of rectangles was much larger. Right? If this were 100, that would be no problem. You just put 100 here, 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 and then you do the arithmetic. So the arithmetic is a little bit harder, but it's much better than writing out 100 terms in this huge sum up here. So let's see. So I guess maybe we can do one more step of this arithmetic. So 1/2 times 4 plus, let's see, let's simplify here. So cancel the 2. So 5 times 2 is 10. Plus, let's see, cancel a factor of 2 here. So in the denominator, we're going to have a 1 over 12, and in the numerator, we have 2 times 5, which is 10 times, oh boy, 9, so 90. So you can see this arithmetic isn't too bad. So we'll call that done. If you actually wanted to know what this approximate area is, of course, you'd work work out all of this arithmetic, but we have bigger fish to fry. Okay, let's try this one. So approximate the area under 2x minus 1 on the interval from 2 to 5 using 6 rectangles and left-hand endpoints. All right, so we're going to use the same idea. We need to write out this Riemann sum. The area is approximately. Now, since we're using left-hand endpoints, our sum is going to start at 0 and go up to n minus 1. And we're going to do f of a plus I delta x times delta x. Now delta x is b minus a over n. So that's 5 minus 2 over 6. And this gives us a half again. I've worked it out so that we get delta x to be a half because things can get really messy if delta x is too messy. So I'm making it so it's not too messy. All right, so this sum gives us the sum from I equals 0 to n minus 1 of f, and f is the function that multiplies by 2 and subtracts 1. So we're going to multiply by 2 and subtract 1. And then a plus I delta x, a is 2, so 2 plus 1/2 I. All right, so this whole portion right here is f of all that stuff. And this a plus I delta x is just this part here in blue. Okay, and then times delta x, so times 1/2 all the way on the outside. All right, so now we can work on evaluating this. Exactly how you evaluate this sort of Riemann sum depends on what the sum turns out to be. For this one, we can start by moving this 1/2 out to the front. And then sum from I equals 0 to n minus 1. We can multiply out this stuff on the inside, so it looks like we're going to get 4 plus I minus 1. So this is 1/2 times the sum from I equals 0 to, oh, I wrote n minus 1, but n is 6. So this should be a 6 right here, and right here, and also right here. All right, so 6 minus 1 is 5. And on the inside we have 4 minus 1 is 3, so 3 plus I. All right. Now, once again, since the number of terms in this sum isn't too large, we could explicitly write out this sum. Let's do that, I guess, just to see what we get. So when I is 0, we get 3. When I is 1, we get 4. When I is 2, we get 5. When I is 3, we get 6. And when I is 4, we get 7. And then when I is 5, we get 8. All right, so this is 1/2 times, let's see, 7, 12, 18, 25, 33. So 33 over 2. Or what's that? I guess 16.5 if you prefer it that way. But let's use the properties of sigma just because I think that's an interesting exercise and because you never know, it might come in handy later. I'm foreshadowing there. So this is 1/2 times, and again, we can break up this sum. This is the sum from I equals 0 to 5 of 3 plus the sum from I equals 0 to 5 of I. Okay, so 1/2 times. Now there are a couple ways to handle this first term. One is just to realize, well, look, this sum is actually 3 added to itself 6 times, and so that gives you 6 times 3. Okay, for this second term, the formula that we had for the sum of the integers, right, for the sum of I, actually started at 1 and not at I equals 0. So it seems as if we can't use that formula immediately. But what we can do is write out explicitly the I equals 0 term. The I equals 0 term is 0. And then let's write out all the rest of the terms. But rather than writing out the rest of the terms separately, we can actually bunch them all together. The rest of the terms are the terms from I equals 1 up to 5. And we're summing I. And this piece, this last term here, that is exactly what we have a formula for. So now we can use our formula. You see, this extra I equals 0 term actually just gave us 0 in this case. It doesn't always, but in this case it did. Okay, so 6 times 3 is 18 plus, and then the sum from 1 to 5, so it's 5 times 5 plus 1 over 2. So 1/2 times 18 plus 5 plus 1 is 6 over 2 is 3. 3 times 5 is 15. And we get 18 plus 15 is 33. So 33 over 2, which is exactly what we got before. So everything is working correctly. So the important thing about Riemann sums isn't so much being able to evaluate them like this, although that is important in some contexts. To get a quick and dirty approximation for the area under a graph, you can, people do actually use Riemann sums in this way. The important thing about the Riemann sum is now that we have this expression for the area under the graph is approximately the sum from I equals 1 to n of f of a plus I delta x times delta x. This is an approximation, but remember once we had an approximation, our plan was to improve the approximation and to take some kind of a limit to improve the approximation and turn it into an exact result. So if we draw out sort of our general sketch of what this Riemann sum is doing, right, we want to figure out this area. So this Riemann sum breaks this interval into subintervals and then uses rectangles like this. So what could we do to improve the approximation? Well, you see, this is an approximation because these rectangles are so wide that they sort of stick out past the graph. So what we should do to improve this approximation is use more rectangles. If we use twice as many rectangles, then these rectangles could follow. Let me do this in a different color. If we use twice as many rectangles, the rectangles could follow the graph much more closely, like this. You can see that the extra bits of area that we're getting are much smaller than they were when we used fewer rectangles. So to improve this approximation, what we should do is just increase the number of rectangles, and that's n. So, right, all we need to do to make this better is increase this number here, increase n. Well, how big should we make it? Well, I mean, if we ever stopped increasing n, then we'd still have some little corners of our rectangles sticking out past the graph. So what we really want to do is let n increase without bound. And that sounds like a limit. So what we really want to do is take the limit as n goes to infinity of the sum from I equals 1 to n of f of a plus I delta x times delta x. This is really the definition of what we will mean by the area under the graph. And this crazy looking limit has some interesting properties that we will investigate in the next section.